which has started now. I will speak very loudly, and I hate this. All right, good afternoon. Thank you for being here for your final shot of knowledge for this day. We're going to be talking about defensive programming, which essentially means how to make sure that your code doesn't break as easily as it otherwise could have. My name is Bart. There's a lot of hair behind this bun. I'm primarily a backend developer. I've been doing Drupal for about a decade. Contrib, core. My first version was about 4.6. It looked a lot worse back then. And I've become really interested in defensive programming over the years because I've made plenty of mistakes in the past, and I've learned how not to make some of them anymore. And some of these practices I want to share with you today. In essence, my definition of defensive programming is how can you prevent as many problems from popping up by just making things more simple. And if things do go wrong, how to make error handling more helpful so that if something goes wrong, you can fix it more easily, more quickly, with less frustration. And before we continue, it's okay, things go wrong. Whether you work on core, or whether you publish an open source package yourself, or if you work for a client, things break. We're human, we make mistakes, and that's fine. This is when it comes to code, but it's also when it comes to working with other people. Sometimes we have a grumpy day and someone says something that they don't really mean. What's important is how you deal with the problems after they've occurred. So this is primarily about bugs. Bugs take many different sizes and shapes. Sometimes you see it coming, sometimes you don't see anything coming, and it takes you a long time to search for it. And one of the in open source, one of the most interesting situations in which bugs can show up on your radar is when somebody uses your code in a way that it's not supposed to be used. It's very often happens if you maintain an open source package and someone comes into your queue and says, hey, I've got this problem. You're like, you're not supposed to use my code like that. But it might also be yourself or a coworker who just made a tiny typo. And unexpected usage should occur only relatively few times because your code should be relatively self-explanatory. If you look at someone's function, someone's public API, it should be relatively clear how to use that. But sometimes, like I said, there's a typo. Sometimes someone wants to do something with your code that you did not anticipate. Sometimes they want to stretch what you built to its limits. That's a good thing. That's, again, the unexpected usage. When someone shows up in your queue and is like, hey, I'm trying to do this really awesome thing. Can you help me? You can reply in two different ways. Like, nah, it's not what it's supposed to do. Or, yeah, let's see if we can support it. Or if it is not supposed to be used like that, and someone's really frustrated with the problems that showed up, maybe we shouldn't support it, but we should improve the error handling to make sure that whenever someone uses your code the wrong way next time, they're just slightly less frustrated. Which brings me to helpful failures. They reduce a hell of a lot of problems in our daily lives. It's not fun to go after bugs. It's not fun to have to fix bugs. If it's really difficult to do, it can become stressful, it can become boring, it can get grumpy. At the very least, it takes time, which is bad for scheduling. Time is money. And because we don't work on our own, we work in teams for clients who may have their own clients. Maybe you work with another company for the same client. The longer something that is not expected, because these are unexpected problems, the longer it takes, the more you block or delay someone else. And this, again, mistakes are made, so let's assume it's by accident. But it means that the whole process of getting something done is disrupted. People can get grumpy. If it happens all the time, maybe you can get a burnout. Nobody wants any of that. And this is in no way about burnouts. But just to state, the less problems there are and the easier they are to solve, the happier we all are at the end of the day. One of the easiest ways of preventing problems is to keep things simple. Anything that's simple has a much lower chance of breaking down on something that's really complex. But simplicity can come in many different forms. For instance, it's not the same as keeping things short. Maybe more code, or more code, and it doesn't have to be really complex. It can be boilerplate code as well, can mean that the whole thing is simpler and therefore easier to debug. Splitting things up into multiple parts gives you more code, but also means that when you do find a problem, it's much easier to locate in which part it really happens. So if we look at this, this is a small piece of code with 2 conditions and a loop. And I call this relatively unreadable code. You've got multiple conditions in the same statement, or same if statement. You've got nesting, so you've got a loop inside of an if statement. And this is just 2 levels of nesting. There are functions even in Drupal core that go 5, 6 levels deep. And then it can become really difficult to figure out where exactly something's happening. Or to expand the code. Like if you need to add something, where do you add it? Do you want to grow the levels of nesting? Do you want to make that inner loop much bigger? Or should we split it up after all? So we take a look at this, which is relatively short. It's only a couple of lines. But I call this really wide code, because we've got nesting and we do multiple things on the same line. This is what I call narrow code. Per line, we do only 1 or 2 things. It makes it much more readable, because that's what we mostly do. We spend more time reading our code, each other's code, trying to understand it, and not just when we do a peer review, but also when we hunt for bugs. So that is a process that we should optimize for, to make it less frustrating than it could otherwise have been. And we do this by splitting things up, by tearing them apart. We do one thing at a time. So we have one condition, and if that passes, okay, then comes the next condition. And eventually, in this example, comes the loop. And we use early returns for this. So the moment we know that our code should no longer continue its execution, we stop it. That's why, if status is false, we know we don't have to do anything else. Let's get out of the function. If there are no items, maybe a bit of a silly example, but we stop. So even when we test, we know that if there are no items, this code will never actually reach the loop. So if something's wrong, we know that the problem lies way before the loop. And if we go back a little, variable naming is really important. Make sure that if you name your variables, name your functions and your classes, that they are explicit, that they tell you what exactly they do. And so this is, apparently, keys in this array are priorities. We didn't know that because we had $K, or we have $key. It's not very readable. Of course, we're looping through an array, or a list, or a map, whatever you want to call it in different languages. We know it's the key. But what does it mean? What does it do? Is it an ID? Is it a name? In this case, is it a priority? But don't be afraid to use names that are slightly longer. The most important thing is that it's not ambiguous. If you have multiple variables that contain very similar types of data, for instance, if you have a list of users and you're filtering them, and you put the filtered list into another variable, give it a name that says that it's users. But how is it filtered? How is it, maybe it is the actual set of users that are administrators of your site that you actually want to perform an operation on. So it's not just a list of users, it's a list of administrators. Thinking about this, like slowing down and considering like what's in here, what should I name it, helps you conceptually understand your code much better. And it's good to do that before you put it out there. So it makes it easier for your coworkers, whether it's in your company or in an open source project, to understand your code, to review it, and to eventually, hopefully, approve it. So readability, as I said, is not just for designing the code, for reviewing the code, for bug hunting. And we can summarize that in the term maintainability. How easy is it to keep this code running and to improve it over time? What does it cost in money, in time, in frustration to figure out what's going on? to maybe extend it in the future. This ties into, again, scheduling and budgeting. So when we write the code, we need to make sure that it is good enough to perform these tasks in the near future, or for a lot of us also, in the long term. Something like Drupal has been in existence for about 15 years. A client site, or even like a short-lived marketing site, might only see the light of day for about a month. So depending on what you need to spend more or less time on making sure that you can keep performing those tasks for the duration of the lifetime of the product you're building. So apart from maintainability and readability, what if things do go wrong? So let's assume that once a week you find a nasty bug that is relatively hard to resolve. So you want to be notified of that. You want to see an error. And that error can be an actual PHP error or an exception, a log message. You want to be notified of the situation that is not as it's supposed to be. So the first step, of course, is where did it go wrong? And it's important to realize that if you get an error message, that might not describe the root cause of the problem. If your caching layer tells you that it couldn't cache an item because it couldn't connect to the database, you might get a caching layer exception, which under the hood is caused by a connection error to the database. And again, that might be caused because the disk is full. So it's very important to log root causes of errors and to chain errors. We'll see more about that in a little while. So once we've figured out what the root causes of the problem is, where the root cause comes from, what is it? What is the problem? What are we trying to do that went wrong? Why did it go wrong? Well, the underlying problems, what are they? But also, how can we potentially fix this? How can we, given this problem, we know what it is, what steps do we need to take to fix it in the shortest amount of time with as little as possible frustration? And you can do that by documenting your errors. And this is an example from Elm, I think. And there's a little typo. Instead of the constant true, or the symbol true, we typed tur. Elm can't find it, but because it tries to give you a useful error message, it already failed. It already stopped the execution, so it can take a little bit more time to build this useful error message for you. So it scans the code that it's already parsed, and it sees, oh, hey, we do have a symbol called true. Did you happen to mean that one? Because it's very similar to the one that you mistyped. This is an example of an error. It's very clear where it comes from. It's on line 8 in the code. It's right there. It's this part of the line, and it has instructions of how to potentially fix it. If you throw an exception, you can include a link to a documentation page. You include the correct terminology that someone has to search for. Give people like a little boost on their way to solving the problem. To prevent problems, we can use things like validation. Validation comes in a lot of different forms. But basically, you can say that we validate something to make sure that before we start with anything, we know that the information, the data we have, is what we need, is what we expect. One example is input and output of systems. And systems can be anything from a tiny little function to an entire network of linked systems. If something goes in and out of a system, you need to make sure that it is of the format that you can work with. An IP address or an email address is a string, but not every string is an IP address or an email address. So you want to make sure that even if the data types on a programming language level are good, the actual content of the data you're working with is also of a format that you can work with. So input is basically anything coming into the system. To give you a very visual example, if you submit a form online, if you register on a website, that is input into the system. If you give a system your email address, they need to make sure that it is of a valid format, because that email with your registration details needs to end up in your inbox. And if it doesn't end up in your inbox, it's not necessarily that problematic for the website itself. It's annoying. But they may, if they send an email to a non-existent address or an address of an incorrect format, receive a flood of emails in their system from their mail service saying, like, can't send it. Flooding logs are a problem. fills up the disk, breaks your MySQL connection. Similarly, output can also be validated, depending on what you want to do. The computer science theory generally says be conservative in what you send out, so make sure that what you send to another system or another person follows the rules as strictly as possible. But if you get something from outside, try to be liberal. But even if you get something that you can, or that you try to interpret as well as you can, the moment you can't work with it, throw an error, throw an exception. Let people know that at that point, the situation is fatal and your code can no longer deal with something. Validation can, in its very simplest sense, be done using constraints. And a constraint can be a string length. It can be a regular expression. Many different things. Basically, you can have a dynamic constraint system where in the code itself you say, oh, is this string more or less than n characters long? Or you use an API with a builder pattern, like make a constraint, add a child constraint. It must be minimum 10 characters long, maximum 20 characters long, must contain an @ sign, and you build a collection of constraints that the data has to match, and if it doesn't, it fails validation, and you halt your execution of that particular function. But you can also use more static systems that eventually, conceptually, validate the data in the same way, but you can store that in a file. So when you want to validate HTML or XML or JSON, you have schemas or doc types that you write down in a file, and most languages can read them and validate a data set against its constraints in 1 or 2 lines of code. So you have very quick, very detailed validation, and you know exactly if the data you receive from that JSON API over there is something that you can read from. And the benefit of this is that because validation takes 1 or 2 lines, if that passes, you know that elsewhere in the code, you no longer have to build in additional checks. An example in core, for instance, is because our render system works with arrays. Arrays can't really ensure their own integrity. We keep having to check, like with isSet, is this property set? Does it have the right value? So our render system and our form system, they're both littered with these checks. If we were to use a constraint-based validation system, we could ensure in a similar way that our data is correct, but the actual logic of the code can become much smaller. It's much easier to read, it's much easier to debug, leading to, again, decreased frustration and less time spent on fixing problems. Another much simpler way of validating is to just use a whitelist or a blacklist. If you use a form element in Drupal, a select list, you have hash options. That's just a list of allowed values. If it's not in the allowed values list, it's not valid, fails straight away. Some languages, not PHP, have an enum or enumeration type. Works in the same way. Type checking is much more low level. It works in a language itself, if the language supports it. So JavaScript doesn't, for instance. JavaScript can, well, if you have an if condition, but like a type hint like you see here that says, oh, hey, if you call this function with these 2 parameters, they have to be of these types. That's the language doing the validation for you. If it's not an integer, it will fail. So, similarly, if the return value is not an integer, it will also fail. And this is, especially the return value, it's really useful if you work with interfaces or prototypes, where the specification is separate from the implementation, and you want to make sure that all the implementations follow the standards that you set, your public interface. This is usually really fast. If you have a language like Python, it supports type hints. They're not enforced during production because in the Python world, people believe that this type of validation is too much of a performance hit during production. But there are many tools that allow you to enforce this during your tests. Assuming that in production you will not or hardly ever get any weird edge cases, which we all know is wrong, this works well. It's fast in production, and it's strict and explicit in what's wrong during your test runs. So I said something about addresses, IP addresses, email addresses. If you pass them on as a string, because that's what they usually are, you still don't know if they're valid email addresses or IP addresses. If you pass them on as a string, every function that takes it as input should theoretically, if you want to have proper validation on every level, validate the address over and over again, which doesn't only mean that you have to type all that code, but it also incurs a small performance hit. So one thing you can do is to make this a value object. And this is a Python example of a class called email address. And you see the init function that takes the email address, which is a string, and then it uses an email address validator. And if it's not a valid email address, it throws an exception and it prevents the object from being instantiated. If it doesn't fail validation, so if it is a valid address, it will not raise an exception. It will continue instantiating the object and set the email address in an internal variable. We can then pass on this object to every function, and the only thing every function has to do is to check if the value it gets is an instance of this class. And then it knows that, oh, this class can never be instantiated if the email address is incorrect. So if we do have an instance of this class, we know that it is correct. So then you can validate your function input by simply using a type int like we have over here. So instead of int, we would have like email address, that's the name of a class. And you no longer have to add an additional line per function to validate your data. This is a good way, especially with more complex data, of ensuring that what you pass on throughout the system not only can't change, but also is always correct. Because the object can never exist if it's not correct internally. If things do go wrong, there are exceptions. And exceptions are basically fatal errors. However, they are fatal only within a particular part of the code, within a particular scope. If one function can't deal with something, it's a fatal error to that function. But the calling function may be able to handle a problem of this type. So if you have a call stack, you start with the first function that in your code execution, which calls another function, which calls another function. You get a chain of functions calling each other, called the stack. And maybe at the end, the 10th function throws an exception because it doesn't know how to deal with the problem. But the 5th function does know how to handle it. And from that point on, it resumes execution of the program. It recovers from the program. Maybe it can't handle it after all, and the exception bubbles up to the beginning of your program. And if it's not caught, if it's not handled, then the program just stops. Because then nothing in the program, then it's fatal not only to that one function, but it's fatal to the entire program. So throwing exceptions or raising exceptions is as simple as using the throw or raise keyword, depending on the language, and then your exception is in most cases an object. JavaScript's a little different, but in most languages it's an object which contains metadata of the problem. Location of where the problem occurred is always there, a stack trace is always there, like which functions were called leading up to this problem. But you can create your own exception classes. This is an example from PHP. But functions or exceptions are just classes that can extend each other. And any class can have a constructor, can take arguments. So what you can do is you can create objects that when you throw these exceptions, because you encounter a problem in your code, can contain all kinds of metadata. Maybe you are receiving an incorrect web service response and you want to add information to that exception about the request you send out to the web service, the address, what post data was involved, anything that might help a developer debug the problem, find out exactly what went wrong, and spend as little time as possible between observing the symptom and committing the fix. So make sure that whatever you do with error handling, it's not just an indicator of something that went wrong, but also of how it can be fixed. So these are fatal problems, but not always. Some part of the code might consider a missing database connection as not really that big of a problem. Like, all right, cool, we'll log it and we'll continue with the rest of the program. And that's called catching exceptions. This is roughly the syntax. Most languages have a syntax like this. In your try block, you put the code that you want to execute and that might cause a problem. In the catch block, you catch the exception, but you only catch the exceptions that you can actually handle. If you have a database connection error and you look, database connection error is another problem for me, you write a catch block for that type of problem. But you can have multiple catch blocks. So you can extend this list with try, catch, 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 finally, and then you have 3 catch blocks for different types of problems. If an exception is thrown that you can't handle, don't catch it. It will bubble up to the next calling function, and they'll see whether they can handle it right there. Finally, there's finally. And it's really useful because sometimes you need to perform some cleanup tasks. Maybe you need to read or write to files. Files might not exist, might cause exceptions if you try to read them. But you want to close the file handle whether it succeeds or whether it doesn't succeed. You can do that in your finally block. If you want to perform complex database operations in one transaction, your finally block can do a rollback, clean things up.
That's a question.
Sorry? Yeah?
In D7, there's entity metadata wrappers. Are you familiar with the exception handling?
Can we keep this? Is it about that particular slide, or is it in general questions?
It's about error handling, catching errors.
Mm-hmm.
D7. Yeah, so it's about that specifically, yeah, catching exceptions. My experience is that it just fails. Like it doesn't. Is the you know if there's some property you can't retrieve or whatnot, or it just fails, you don't get a white screen. I always wondered why are they using exceptions here? It seemed to me the opposite of what you're saying, because basically then you end up with a white screen, more or less.
Yeah.
Is the idea that
the white screen, as a reason for that, I'll go to the next slide and explain it. So the question was, if in D7, if you've used entity metadata wrapper from the entity module, and you try to access something that doesn't exist in the entity, like a field that's not there, you get an exception which results in a white screen. And this has to do with exception bubbling and the exception not being caught, generally. Drupal tries to hide fatal problems that cannot be resolved from the visitor. So what happens is that if an exception is thrown and there is no part of the code base that catches the exception and says, I can deal with this problem, it goes up the stack to the beginning of the program. And for Drupal, the beginning of the program is index.php. If it's still not caught there, what the PHP parser does is it treats it as an uncaught exception. And an uncaught exception is fatal for the entire program. It doesn't mean that it crashes. It means that the parser or the compiler or runtime, it just stops working. And because in Drupal we don't want to show a lot of the internal details of how the program works to a visitor, Drupal does catch it, but it doesn't show anything and it just gives you a white screen, because it's fatal after all. This is not always very useful when developing, because you have to check your logs or you have to mess around with your error settings in order to see the cause of the problem and to see the exception details. With entity metadata wrapper, I've worked with it on one project a couple years ago. It's a little fragile. For us, it broke sometimes when it shouldn't have broken. I'm not too experienced with that part of D7 to know what the solution is, but that's why you get the white screen of death.
Right. Yeah, I was wondering if it was just a misuse of exception, because I don't see what you're gaining.
It's a good use of exceptions. So the question was, is it misuse? It's a good use of exceptions because the entity metadata wrapper can't deal with it. You're trying to make it do something that it can't, and it's like, I'm fatal, whatever. I can't deal with this problem, and it communicates that by throwing an exception. We're not really used to handling exceptions that much in Drupal 7, so there's not really a proper infrastructure in place to catch things in many places. Right. This was the second part of the slide. So a fatal uncaught exception terminates the program. PHP doesn't crash, Python doesn't crash, it just stops the execution of whatever program you wrote. Drupal, a Django site, your custom script, it just ends the whole thing right there and then. Which is partly why you want to use that finally block, so you can clean things up. You don't want to have any stale file handles or half-executed database statements that leave your data in an invalid state. So you would only catch an exception if a particular piece of code says it's not a problem to me. Yeah, something that is, I'm a backender, I work with front-enders, and if my front-end coworker sees a PHP error, they're like, I don't know what to do with this. This is fatal. Whatever. Throws an exception, throws a ball in the air, and I'm like, I'm a backender. I can deal with PHP errors. So to me, it's not a problem. And that's what catching or throwing and catching exceptions is about. You will only catch something that you can deal with. So if they are like, if they throw a front-end exception, so because there's something wrong with their CSS, I'm like, I don't know what to do with this. I'm going the hell away from here, and I leave someone else to do the job. And if there's nobody on the team who knows anything at that point to do with CSS, then the exception gets uncaught and we're blocked. We need to figure out how to deal with it, and the development comes to a full stop because we have a major issue and we need to figure out what to do with it. So that's what I said with this. You can add catch statements, as many as there are problems that you can recover from in this situation. So if you have a cache mismatch exception, handle it here. If there are 3 other types, 10 other types, make these cache blocks for all the different types of problems you can deal with. Because classes can extend from each other, what you can do is you can type hint, right there, on a parent class. Maybe there are different types of database issues that you can encounter, and you don't really care about the specific problems. You just know that any database problem means that I can deal with it by just closing the database connection and reopening it, retrying. So you can have one catch statement that catches a parent class, which represents a whole range of potential problems. And you catch the range of problems by typing it on the parent class because they share something generic. Now, they're all database problems, they're all caching problems, and you know how to deal with these problems in a generic way. Catch what you can handle. So don't make a catch statement that type hints on the parent exception class, because that's what all the exceptions extend, because you can't handle any exception. If you do that, you run the risk of the exception like dying out, not bubbling up to the top where it might be able to be handled or where it might end up in the log. So be really careful with that. So when you do catch an exception, there are several things that you could potentially do, and these are some of the common ones. Like I said, you can close things off and retry. You can log things, send notifications. If you have a white screen of death and it's a really important site, maybe you will want to have a top-level catch block that says, like, no matter what the exception is, if something went wrong all the way up the chain, we're going to send a text message to our developers to fix it straight away. But what you would do is rethrow the exception in the catch block. So you basically pause the bubbling, you perform a few tasks, and you rethrow the exception, or you can create a new exception and throw that one. So you've done your thing, but you still want the exception to bubble up so it communicates the problem to another part of the system. However, always make sure that if someone somewhere needs to look at this problem, that error reaches them. So don't let things die out. Don't have a catch block that's empty, because that's the worst thing you can do. Like, if there's something goes wrong and you have absolutely no information about where to look for, what to look for, or where to look. So the benefits of defensive programming, which is a very, very wide range of approaches that you can employ, is that eventually you'll become faster. Especially if you teach yourself, it takes a while to get used to all of these things. Once you make it a habit, like a second nature, it's easy to add. You start writing a function, and the first thing you do is validate the function input. You know that you are designing a system that needs to pass on email addresses, make a value object, and then use it elsewhere. You need to perform a few tasks at the beginning, and eventually you'll become a lot faster, because you can reuse a lot of these tools. There are entire libraries that help you validate these things. If you use PHP, there's the breli assert library, B-E-R-L-E-I, which has a wide range of checks that you can call. It's just like a static function that perform a lot of code, like a lot of tasks internally to make sure that your data is correct, but it only costs you like half a line of code yourself. And it allows you to fail early. The moment a problem shows up, you want the problem to be observed. You don't want it to happen 10 functions down the line, because then you have to start searching for the root cause of the problem, which was 10 function calls earlier. You want to fail often. So make several points in your code where you validate these things. It all helps you with finding the problem as soon as possible in the right place, reducing the time you need to spend on fixing it. Keeps you happy. Keeps you happy. The most important thing is the entry points of your code, your public API. If you write a library, or if you write a couple of functions for your coworkers to use, that is like the public API. That's stuff for other people to work with who are not necessarily familiar with the internals of the code that you wrote. And you don't want them necessarily to spend time on becoming familiar with your code. You want them to be able to use it straight away, get their job done as soon as possible with the least amount of problems. So these are the points in your code that you have to spend extra care on to make sure that they don't fail, and if they do fail, they do so in a way that's useful. So if you only have a little bit of time to do this, do it in these places. We have 5 minutes to go. Do you have any questions? Yes?
On the screen we had the console output showing if true was misspelled.
Yes.
Was that generated by some tool?
No, that is Elm out of the box. We're all used to PHP and JavaScript, and PHP and JavaScript are not very nice friends to play with because they're very bad at giving error messages. You might remember from older PHP versions, if you had a missing semicolon, it would give you an error with some kind of a Hebrew name. And while I'm sure that Hebrew is a very, very lovely language, most of the people in this world don't speak it or read it. So that's a very good example of an error message that is completely useless to the majority of the people. The people behind Elm decided to put a heavy emphasis on making sure that if things go wrong, the language itself gives you these useful error messages. So it can't tell you that your email address is incorrectly formatted, but things on the language level, like you're using a constant or a function that doesn't exist, it tries to make that as painless as possible. So this is all native out of the box.
I'm sorry, it's called L as the letter L or L?
Elm, E-L-M.
E-L-M?
Yes.
It's hard to write.
It's a functional programming language, so it's, is it used for web development? Or is it Elixir that can do JavaScript stuff as well? Okay. It's not something that I've never written in Elm as well, or either, but I found this a very good example of what we do wrong in PHP and what we should aspire to do. All right, and I want to thank you for coming. There is a party tonight at 8 o'clock. It's on the website. Enjoy your dinner, and if you have any questions, approach me in a bit or tonight at the party. Thank you.